Καλώς ήρθατε σε ένα ακόμα Path όπως σήμερα μαζί μας είναι ο Dr. Philip Rosenberger, ο υπεύθυνος στην τομέα laser της Γερμανικής εταιρείας Pulse, για την οποία σε πολύ λίγο θα μάθουμε και περισσότερα.
Hello and welcome to our podcast. We're so glad and honored that you're here with us today.
Thank you, my pleasure.
Thank you. So, first and foremost, I would like to ask you some questions about Pulse. Tell us about it, about your product Albatros, its key features and the applications of it, everything.
So yeah, since we're a startup and we are quite young, so far we have one product, as you said, the Albatros laser, and it's basically a PhD project turned into a product. So my colleague Natalie, she developed the system during her PhD as an ultra short pulse laser, and you always have to define what this really means. So some people call a few hundred femtoseconds already ultra short pulse. For us, it's 10 femtoseconds. So that's quite shorter, I guess. And the central wavelength is 2 micron, where you have about 10 femtoseconds of oscillation period. So we really have a single cycle laser pulse that we produce with this laser. Sorry, I just have to get rid of something here. And these laser pulses are on top of that what we call CEP stabilized. The CEP is the carrier envelope phase of a laser pulse. It's basically the relationship between the pulse envelope and the oscillating field underneath. And we stabilize this so every pulse that comes out has the same electric field shape exactly to a very good accuracy. And these two features are basically our selling point. So applications are at the moment mostly in the scientific environment. So our customers are other universities. When I say other, we are a company, but we are still so close to the LMU, Ludwig Maximilians University in Munich, that sometimes, it slips. Our customers are universities, and they use these lasers for mostly pump probe spectroscopy. So you have one excitation pulse to start off a chemical reaction or something, some motion in some semiconductor, and then you use a second pulse to probe whatever change you caused with the first pulse. And because these pulses are so short, you can really go you get a very high time resolution. So you can see features on femtosecond time scales. And that's at the moment the most promising market for us at the moment. Yeah.
How come you named the product Albatros? Is there a connection with the seabird? Because we noticed that also the company's logo is a bird.
Yeah, so that has multiple answers. So the first answer to the question why it's Albatros is so that was decided well before I joined the company. But basically, because we have such short pulses, in the Fourier domain or in the spectral domain, our pulses are really broadband. So we have a very broad spectrum from about 1 micrometer of wavelength to about 3 micrometers of wavelength. And so something that is also broad is the wingspan of the Albatros. So it's just I think the bird with the largest wingspan or something like this, and this is why the laser is called that. So why is it a bird in the first place? I'm not really sure about this, because that was also before my time. But what I think the origin is there is a research group at the chair of Ferenc Krauss, where all this emerged, and it's basically called BIRD, Broadband Infrared Diagnostics, so BIRD, BIRD. And I think this is how it came into the company also. And this infrared diagnostics, that's also related to our company. This is where we want to go at some point, not only selling lasers, but selling infrared spectrometers, very fancy ones.
Okay, that's great. So let's continue now with questions regarding your experience in Pulse. First of all, what is your role in the company? And of course, what are your day-to-day tasks? What are you doing there?
So that's an interesting one, because we are a startup. We only we have grown quite a lot. Last year, I would have said we're only 3 people. Now we are 6 people. And when you're so few people, you can have a title or whatnot, but it doesn't really matter, because everyone does everything a little bit, or the roles change depending on what needs to be done and what you have time for. So at the moment, my role is is a lot of things. I just today, I started my day with ordering things, checking up on previous orders, how things are going, because when you produce something, you have to also take care of that. It's not just being in the lab and building lasers, it's also making sure you can build them, because most of the time it's if you have suppliers that are unreliable, you have to really keep poking them every day. So this is how I started my day today. Then I went into the lab, turned my laser on, because what I will do in the afternoon is continue on some development project that I'm doing. So it's a mix between office work, let's say, ordering, forwarding builds to our boss, and going to the lab, building lasers, but then also doing development in certain aspects. So development on the existing project, but also existing product, but also development for future things that we might add to the system or sell separately. So that's kind of that. So it's quite similar to what I did in my PhD, and only a little bit more focused on earning money, let's say. Yeah.
What type of scientists are involved in the project? From which field do they come?
So when we started out, so we are celebrating actually our 2 years birthday today. And when we started out, it was only physicists. And so our CEO is actually a particle physicist by training. And he, after his PhD, joined the chair of laser physics as kind of a science manager, something like this. So he was taking care of budgets, assigning budgets to different subgroups of the group, and things like this. So he was used to doing management, and he's a physicist by training, astroparticle physicist, and he's now doing mostly like strategy, also a little bit of accounting and things like this. And the other two that were there last year with me was also two physicists, and they both were building lasers for the last 6 years or so. So they both did a master thesis and then a PhD thesis in laser physics, and really they did what you would call laser development. They went to the lab and built a laser. For me, it was a little bit different. I was doing my master's and PhD thesis at the same chair, but with a different supervisor. And we were mainly using lasers. So I didn't build a laser before joining the company. I just, my first laser was lasing about a year ago or so. And in that regard, I had experience with optics, but not really lasers in itself. It was helpful that I had worked with very short pulses before, but everything else just came like this. And then since this year, we have 2 new colleagues, and their education is more engineering heavy. So one of them was studying, I believe, electrical engineering, but not quite sure anymore. And the other one did a master in photonics. So it was this dedicated photonics study that he did somewhere. Yeah.
So you mentioned that you're not many years in the company. So were there any preconceptions you had before applying for this job in Pulse? And if they were true or not?
So I'll just tell you how it was when I was applying for jobs. I basically was writing my PhD thesis up, and to make sure that I finish on time, to give myself some pressure, I was applying for jobs in parallel to finishing the thesis. So I wrote a few applications, got invited to a few interviews, and then at the same time, I think Natalie, my colleague, saw that I created a LinkedIn profile, and she approached me and said, "Are you looking for a job?" And I said, "Yeah, for beginning of next year." And then she said, "Okay, there is this startup. How about you work with us?" And then I said, "Okay, I'll do it." Or I look at it, and of course I had some preconceptions about working in a startup, that it's more work than in other jobs, because there are certain tasks and you cannot just delegate. There are no people. You have to do it yourself. If there's a problem, you have to solve it yourself. And it's also usually a tighter budget than in a big company, because if you're not a startup that has a growth potential that is exponential or whatever, or, I know we're not building an iPhone that everyone has in their hands, but it's a very niche market, so that no one will come and give us just millions of euros just like that. So these were the preconceptions, and most of them are true, only that we were lucky to get more money than we thought, just because there were more requests for our product. So we that we were lucky there, that there is more demand than we thought. But it's sometimes actually not close to a 40-hour work week. Then there are times when it's more like 50. It rarely goes above 50, but 50 can happen. What was that the whole question? Did I miss something?
Yeah.
Okay, good.
Perfect, yeah.
All right.
How do you handle the balance between meeting project deadlines and encouraging thorough research and development of the product?
Yeah, that's a tough one. It's so maybe I'll also answer it with an example, because at the moment we are developing some electronics to stabilize two laser systems to each other, that the pulses come out synchronously. And we have a deadline sometime in October. And just 2 weeks ago, I found a way of making this more stable. And I was aware, okay, if we make it more stable, we will probably not make the deadline. So in this case, we have customers that are nice, that are okay, take your time, make it proper, and then you give us a better product at the end. So there it's more about communication. You talk to the people, and try to explain the situation. And in this case, okay, you promise them a better product. Of course, they will say, okay, if it takes 2 weeks longer, I'll take it. I pay nothing more, and I'll take it. And the other cases are not so nice, when you cannot meet deadlines because you're waiting for something. Let's say in our case, we need pump lasers. That's basically just an off-the-shelf product, a fiber laser that emits at 1550 nanometers, which is the telecom wavelength. So there's a lot of products there, but they still have long delivery times. And then you order something and you hope that it will arrive in, 10 weeks, but then it takes 14 weeks, and then you're there a month without the thing you really need. And that is something you cannot really solve, and then you just, okay, whatever. I'll find some other useful way of using the time.
Those situations you told us right now can make the research and development of product like Albatros very stressful. Although there sure are some rewarding things about it. So what do you find most rewarding about working with Pulsed?
So I made some notes on this, but it's just something else came to my mind. And that is when I compare what I'm doing now to working on my PhD, now the projects that I do are more plannable. So it's more engineering projects rather than research or fundamental research projects. So you have an idea and it will probably work. It's not like I have an idea and I have no idea if it works. It's more you can calculate the risk more accurately. And when you can do this, then you're not so stressed out while you're developing. During my PhD, it was always like, okay, I know that I have to spend 2 months on this likely, and then it could go down anytime. It could be a waste of time completely. But here it's more rewarding on the way. When you do a PhD or fundamental research project, you wait, and then either it's really nice or really bad. And here it's okay, I have another step, another milestone, it works, okay, this is good, I'll keep going. So it's not, the highs and lows are closer to each other, which I guess is better for mental health in the long run. Something like this. So that is the rewarding part, that you get rewards more often. Maybe you also get failure more often, but the failure is not so doesn't have such high or large consequences compared to before.
Okay, great. So as you mentioned, Pulse is a startup company, but also it has a lot of research. And has your physics background given you any transferable skills useful for entrepreneurial side of things inside of Pulse? Pulse because you told us that you order things, you see, oh, this product was not good, so we have to change that.
Yeah.
Has your physics background helped you that?
So I would say the physics in itself, not really. If you take away all the technical things and only really the business side, I would say physics alone don't help you. But what does help you is just problem solving. The more you are confronted with problems, I think, the less you freak out because, okay, I can never do this, and the more efficient you also become at problem solving. Then, I mean, sometimes it's really hacky solutions to problems. Like, okay, I have this problem and I cannot put a screw here. I just glue it. I don't care. But you develop some kind of skill of solving problems and also solving them efficiently, I think, especially when so this maybe started only when I did a PhD, because before the projects were more closed off, more compact, doable in a shorter amount of time. And like roadblocks were more unlikely. And then only later, when time becomes really precious, you start becoming efficient. I think, yeah, that's that.
A follow-up question to the previous. You mentioned that you engaged in both research and product design in past, and you have also conducted academic research as a PhD. Do you find differences between doing a research in an academic environment and in a company?
So there are a few differences, I would say. If you do research in academia, then at the end, what you want is always a publication. And if you have the funds, it doesn't matter how much it costs, you just buy whatever you need and you pull through, and you hope that at the end something comes out that is publishable. Ideally, very high impact journal or whatever. And in the company, it's quite different. So, okay, maybe the last thing for the academic research, if usually, at least for my environment, it was like that you didn't really have a hard deadline. So you kept researching, and then when you were close to something, bro, then your professor started nagging you. Okay, come on, can you write something now? And I was like, no, it's not enough. Okay, but we have to write a paper. And then you get, at some point you get pressure, but it's a really it's a curve like this: no pressure, and then a lot of pressure. As soon as they smell like, okay, there might be a publication, you get a lot of pressure. At least that was the style in my group. Not really enjoyable, and also not. It will not produce the best possible paper. It will produce a paper, but yeah, that's a different story. And in research in the company, you have as your boundary conditions at the end, it has to pay off. So you don't do research that you don't think you can sell. At least we cannot afford to do this. Larger companies for sure will just try out things and throw money at something. And then if it works out, fine. If it doesn't, also fine. And they will not go bankrupt because of this. But for us, since we are so small, we really need to think twice if it makes sense to invest time and money into something, because both things are very scarce in that regard. Yeah, that's that. So, but this also means, as I said before, that the development projects you do, they are more realistic than in academia. Usually in academia, you shoot really for the highest possible thing, and for the company, like, okay, let's try something that will probably work.
Yeah, of course. Because it's product and companies need to use it in order to be used. Yeah.
Yeah.
Anyway,
yeah.
So now we're going to continue with questions regarding your career. And first of all, let's begin with your PhD, as you already mentioned, and tell us about it. I mean, the topic. What was the topic of it?
So my topic was strong field. So I'll not say the title of my thesis, but the topic was strong field ionization of nanoparticles. So dielectric nanoparticles, mostly silica nanoparticles. You take a strong laser, you ionize the surface of these particles, and then what we did is we looked at the emission of ions. So everything in a vacuum, spherical nanoparticles. I always try to make the joke that it's the most physics experiment you can do because you have spherical things in a vacuum. And yeah, we shoot it with the laser. Then what you get is you get field enhancement patterns on the surface. And yeah, that's just can imagine it like this. If you have a very small particle and you put it into the focus or you put light on it, you get a dipolar response of the thing, and then it grows, and at some point the light will get focused like a lens, and that's the hand waving explanation for why you have field enhancement. But this dipolar thing grows into something that is focused, and this mapping between size and where the field gets enhanced on the surface we used for measuring the particle size, as it was just a byproduct, and creating with some fancy light fields, more complicated field enhancement patterns. And what the original idea was to look at surface chemistry, because we could detect the ions that get released. So you have to imagine spherical nanoparticle, get ionization at top and bottom if it's a very small one. And that means you remove a lot of electrons. And this is a dielectric nanoparticle. So the charges are quite static. So electrons are gone. And then you have a lot of positive charge left on top and bottom. And this positive charge there will also try to get into some equilibrium. And in this case, equilibrium means everything that is not bound very tightly to the surface. Like, for example, an OH group. So on these silica nanoparticles, SiO2, the surface has typically plenty of OH groups. And this OH group will then start emitting a proton, because that will reduce the surface charge. And at some point, you have an equilibrium between how strong this OH bond is. So you need some positive charge to release a proton, but that will reduce the positive charge on the surface. And it keeps going until the bond is basically too strong and you have some positive charge left. And that's what we looked at mostly. We tried to find some fancy reactions, like this proton emission was one part. It took some time until we understood where these protons come from, but let's say it never really, there was never really something really fundamentally exciting about these surface reactions there. It was mostly about how the charge migrates and so on. That were the more exciting topics. But the chemistry, the initial idea, never really brought anything fruitful. But it doesn't matter really, as long as it's interesting. I would say it's fine.
Okay, so was there anything from your PhD that helped you secure your current job in Pulse?
So mainly connections, I guess. It's really, I'm not a good example here. So that because the Pulse job, Natalie just came to my office, and I knew her from basically the beginning of my studies, and she developed the laser as her PhD project. And so it helped me that I knew her in that regard. But if I think about the other jobs that I applied for, what they needed specifically was someone who could program and knew a little bit about physics. but really the programming was at that time more important to them. So this one job, for example, was for Zeiss, the big optics company in Germany, like ZEISS, and they do most of their business nowadays with semiconductor manufacturing technology. The SMT is their sub-branch, and they are heavily looking for people who know about XUV radiation and who know about how to probably they don't even need you to know how an XUV mirror works, but they produce these XUV mirrors for lithography. And in the quality control department, they have so many open positions because the precision that they need for these mirrors to then produce at the very end, like, microchips, sell these things to lithography machine manufacturers, and they then produce the chips for Intel, for TSMC, for all these companies. And in the quality control department, they looking for jobs like crazy. So this is every second job or so was related to that somehow, but that's also specific to the location because they are located, I think, 2.5 hours away from Munich. And so they try to bring in people from everywhere, but they are a little bit in a rural area and no one really wants to move there. So there are also companies who would then basically be in Munich, but they work for Zeiss. So Zeiss would give some software consulting company some, job, or I don't know the word now, but, and then you work in Munich for a different company, but the company works for Zeiss. That's there they really just need programming skills and a little bit of optics.
What sparked your initial interest in physics, and specifically later in laser technology? Were there any figures or mentors that inspired you?
So I have to start it early, I think. So it's probably the interest in physics was sparked in school. I had one really good physics teacher who just knew how to tell a good story, I think, and make things interesting. And then, because I didn't really know what to study, I wanted to do something technological or technical or whatever, something with math. And so I signed up for physics because I didn't want to decide for one engineering topic, for example, or one thing. And yeah, what do? You go for the thing that's the broadest. And to be honest, in the beginning, I thought lasers are boring. I never really planned to end up in laser building or laser physics in general. It just happened. So it happened because I did a bachelor thesis in theoretical physics, something solid state, not important what the topic was, but after that I thought, okay, I don't really want to sit in the office all day and run simulations and wait until they are finished and then do data analysis. So I was looking for experimental physics groups that need master's students when I was at my master's then. And I just happened to be in one lecture that was semi-interesting, but the professor seemed really nice. So that's my later PhD supervisor also. And I just asked him, do you have a master thesis? And he said yes. And then the topic was already related to lasers. So we were using lasers for this strong field ionization stuff. And this is how I came to the chair of laser physics. And then the rest you already know.
Okay, so that was a great story, actually. And now a more fun question. What career did you want to pursue as a child before school? You told us that in school you said, okay, I want to be a physicist, but before
before that, it changed a lot, I guess. So all the classics, firefighter, astronaut, whatever. But at some point there was some show on TV about some kid who had a lab, and this guy had a spray that makes you invisible, and I always thought that's really cool. So then I was looking forward to having chemistry in school, and I wanted to be like something like that. I didn't really know what it would mean to be a scientist, but I found this spray that makes you invisible really cool. Yeah, but then later in school, I found that chemistry is not really my cup of tea. Too many things that can happen, and
Exactly.
yeah. So then it, yeah, my interest in math then led me to physics, let's say.
We're going to stay a bit more in the past, but now from your current perspective. Looking back, what advice would you give to your younger self at the start of your career?
So I would give one piece of advice to myself when I started studying. So just after school, I was not really sure if I should do physics because of, yeah, it's not a straightforward career path. If you study mechanical engineering, you know that you will end up a mechanical engineer at some company. I don't know, there are enough. That's like easy. If you do electrical engineering, you become an electrical engineer, also easy. But if you do physics, I was always worried, okay, what will I do afterwards? I have no idea. And that made me a little bit uneasy about going ahead with the studies, and also made me look into, jobs that were offered on the internet. I was from time to time just typing, okay, physicist, Munich, and then what you see is consulting. I was like, oh, I want to do something that's a little bit more applied. I wanted to still stay with technology and not just make spreadsheets and PowerPoint presentations the whole day. And the advice would be, don't worry. It's fine. There is enough to do. It probably helps if you have some skill apart from physics. So programming, for example, everybody needs that. And then it's easier to get into a more technical job, even if you're not at a startup that's a spin-off of the university. So I have a friend, for example, who is working in Munich at a company, I forgot the name, Quantum Space Systems or something like this. So what they are developing is some quantum cryptography hardware that you can put on a satellite, and then you can do quantum encrypted key exchange between some station on the ground and a satellite or something like this. So something crazy. Yeah, there are cool jobs like this. It's just, you have to look for them a little bit, and probably they also, yeah, don't be disappointed if you don't get it, because like there are not a lot of them, and usually they are at the startups, and usually they don't need a lot of people. But there is a good chance that you will end up with a nice job if you look for it. Yeah.
That was a great advice, actually, because a lot of students don't know if they want to pursue the career in physics or any other field. So it was very good advice.
There is maybe one more piece of advice for when I started my PhD. I started it because, to be very honest, I was just too lazy to look for jobs, and I had the offer to continue in the same group. And the advice here would be, only do this if you have a well-defined PhD topic, because the beginning of my PhD, it was not defined very well. And then you end up not wasting 2 years or so, but you have just unproductive time, and this will make everything longer. And then at some point you will get annoyed, and then it's not fun anymore. That's a PhD advice number one. Make sure your topic is defined. And PhD advice number two is, make sure that you can reasonably assume that you will have a supervisor who is working on the same project, or at least knows about the project, at least as well as you do. So that was, in my PhD project, I was alone a lot. So it was really a secluded topic from the rest of what the group was doing. So I couldn't ask my other PhD colleagues, and I didn't have a very close supervision. It means you have a lot of freedom. You get to do a lot on your own, but then it also takes 5 years until you are finished. If you don't like that, then make sure that there is some structure in the group where you do the PhD, that there is the boss level, and there's maybe senior researchers, maybe then you even have a postdoc, and then you have the PhDs. And for us, it was like boss PhD students and no intermediate layer. And it's fine, you will get there, but it makes things more inefficient. So, yeah.
Okay, so the next question will be about how do you balance your work with personal life, because you told us that you have a lot of tasks and you spend a lot of time in working, but of course you need some personal time, and how do you balance that?
Yeah, so the times when there is a lot of work are usually concentrated. And I made a deal with our CEO that, I just keep track of my hours, and then when there is less work to do or less urgent things, then I just take time off. So that's, I would say, the ideal solution. And it actually works. So I just came back from a few days off that I just took from my overtime budget, basically. And then you may have a few weeks where you have, I don't know, 45 plus hours, but then you also have weeks with only 20 hours because you can take it off. But that's really luxury, I would say. And probably it will at the end still be that my overtime becomes more and more because, there are things to do. But let's see. So this is quite new now. And then, yeah, it's balancing things. For me, it helps that I live quite close to the workplace. So my commute is only 20 minutes, and that helps.
Right.
Definitely.
Yeah.
Do you have any hobbies or activities that you do and help you unwind and stay creative?
Yeah, so for me, that's a clear answer: sports. Anything from cycling, hiking, rock climbing, something like this. So that's what keeps me balanced, and I really need this. I think other people are different, or everyone's different, but sports just works for me. Something monotonous. Go on a bike and just cycle for 2 hours, and then get into the tunnel of not thinking about anything, but just keep that pedal going.
Okay,
that sounds perfect.
Yeah, actually. So our last section of this interview will be about laser technology, which is a new field and very rapidly evolving. Sorry. So how do you stay updated with the last developments in this field?
So when I have time, I just try to look for publications, but mostly for us, it's like this, that we have an idea of what we want to do, and then we start looking into the newest research on that exact topic. So I am subscribed to a few newsletters, but I really don't read them a lot, because then you come to work and you have 5 emails of that don't interest you, and 5 or 10 that do interest you, and then I usually get rid of all the newsletters. So but I think that's just my style. And other people are like Natalie, my colleague. She's really staying up to date with that and looking into these things. But for me, as I need the information, I get the information. So if I want to know, for example, how I can improve our laser system, how can I make the mode locking more reliable, for example, I just look for papers on mode locking and then go for the newest, the greatest, and those that fit the best. Yeah.
What industries or sectors do you think will find the most significant impact from advancements in laser technology in the next decade?
That's a tough one. For us, we hope, of course, that it will be infrared diagnostics. So we built this infrared laser that can be used to efficiently generate even longer wavelength infrared light. And then if you do it right, you can do infrared spectroscopy with about 50 times more sensitivity than you can do today with available systems. That was also a measurement technique that was developed here in Munich at the chair and at the Max Planck Institute for Quantum Optics. And yeah, we hope that this will be the largest impact, that we can use this infrared spectroscopy to get a medical tool out there to analyze blood samples, basically. Hopefully cheap enough and reliable enough and fast enough that it makes economical sense. And then you can do a personalized health monitoring. So you would go to a checkup every year or so, give a drop of blood. They don't really need more than this. And then the doctor will tell you if maybe you have an increased risk for, I don't know, a certain type of cancer. So that the research at the moment that's going on in Ferenc Krause's group is mostly about lung cancer, because it seems that it might work. And yeah, we'll see. But there's also a study going on about exactly that diagnostic tool, where they have 10,000 people and they just follow them for the next 10 years. And of course, there will be people who get sick within these next 10 years out of 10,000. And then the hope is to not only detect the things that we already know will work probably, but more than that, that you get a really broad and simple information about what's going on with your health status just by measuring the infrared spectrum or the absorption spectrum of blood or blood serum with high accuracy. And so yeah, I hope that is the most disruptive thing that will happen. We will see. You never know.
That's so interesting, actually. It will be very helpful for the medical field, actually. Yeah.
So the one other answer would be fusion, but laser-based fusion. But I'm very cautious there to say that it will work. So it looks like right now scaling this such that the lasers are efficient enough and produce pulses with enough power without using so much electrical power that you don't get anything out of the fusion. I'm saying, okay, it doesn't look like there's a laser medium at the moment that can drive laser fusion efficiently. So probably not within the next 10 years. Maybe later, I don't know.
Yeah. Okay, great. So we have arrived in our last question. What legacy do you hope to leave behind in the world of laser technology?
That's probably the answer is similar to the one that I just gave.
Yeah.
We hope that it's not only the ultra short pulse lasers that people use in their labs. Of course, that's also nice. I mean, if they say, okay, that's a cool laser on its own, but if you can really make an impact and for more than just 10 researchers or let's call it 100 researchers in the world, if you can make a larger impact by, for example, this health monitoring, or if you step it down a bit, let's say we make just infrared spectrometers because the health thing doesn't work out in the end. It's just, I hope that we will make a larger impact than just supplying labs with ultra short lasers. That's.
So that wraps up today's Path Talk. Thank you so much that you were here with us. It was an honor. And it
You're
was
welcome.
very enjoyable and helpful, either you.
You're welcome.
So,
and
thank you so much.
If you just keep following our homepage or follow us on LinkedIn or so, if in the future you're looking for a job and you're interested, let us know. So we're still growing, and who knows? I cannot promise anything, but we're always interested in smart people and motivated people.
Perfect. Thank you so much.
Thank you so much.
Right.
Have a good day.
Have a good day.
Bye-bye.
Bye.
Bye. Αυτό λοιπόν ήταν και ένα ακόμα Path Talk. Ευχαριστούμε πάρα πολύ που το παρακολουθήσατε. Επίσης, ευχαριστούμε πάρα πολύ την Infinity Greece που μας παραχώρησε δωρεάν αυτό το χώρο.
Και το λέμε στην επόμενη Path Talk.
Γεια σας.